Okay, recording started. Okay, so let us continue with artificial neural nets. So at the end of the last lecture, we just give a start, right? So I would like to first give a concrete example of the neural network to give us a sense what is neural network, right? So we build a probably the simplest neural network. It's called linear threshold unit. We briefly introduce it when we talk about linear classifiers. So this is the structure of our neural network. So this is just one layer neural network. So at the bottom, I mean, in the leftmost are the input features from the original data. We have 4 features: x1, x2, x3, and x4. And also we append a constant feature 1 to incorporate the bias parameter. And then those features are collected and sent to an intermediate node. So how do those features are integrated? So for each feature, on edge, which connects this feature and the node, the dot product node, we have a feature weight W1, say W1 for X1, W2 for X2, W4 for X4, and also the bias parameter B for the constant feature 1. So the integration is done by first multiplying each feature with the associated feature weight, and then add them together. So essentially, it does the dot product, right, between the feature vector and the weight vector. So after those features are integrated into this dot product, it will then be sent to a second node, which does the thresholding. So basically, for linear threshold units, our thresholding function is a sign function. Take the sign of this score, right? So essentially, the output of this one layer neural network is the prediction made by a linear classifier. So this is the simplest artificial neural network. Right? So the parameters associated with this neural network are the feature weights and the bias parameter B. Right? We have discussed several algorithms to estimate those parameters from data, like perceptron, like SVM. Right? And in general, we can view them, even for perception, we can view them as minimizing some loss on the training data, right? Remember when we talk about perception, the training perception, the update of perception is equivalent to do the stochastic subgradient to optimize some objective function, right? So, okay. So, obviously, this is a although this is a valid example, this is not our major interest, right? Why do we construct neural networks? Because we want to build out powerful expressive classifiers which can easily handle nonlinear mapping, nonlinear classification tasks, right? So the question is that how can we build up more complicated neural networks, right? So I think the amazing point of neural network is that it can use this very
highest percent of coronavirus in the nation.
Any question?
I don't know how to read this.
Any question? Please speak loudly. I didn't get your question.
33 cases per 100,000 people. It is.
I think someone just has their mic unmuted.
All right. Okay. So if you want to talk to others, like your family or friends in your home, but has nothing to do with the course, please mute your mic. Otherwise, it's kind of distracting. I thought someone is asking a question, but it's not. It turns out no. But anyway, yeah. Let's continue. Right. So remember, our original motivation to build out artificial neural nets is to build up very powerful nonlinear classifier, right? The amazing point of the neural network is that it can use this very, very simple building block and use a very simple rule to construct a very complicated model. So how can we do that? So we're going to use this linear threshold unit to build up a more complex nonlinear classifier. How can we do that, right? So the original linear threshold unit, the inputs directly comes from the data, like feature 1, 2, 3, 4, and a constant feature 1, right? So now I want to increase the complexity of this neural network. How can we do that? Instead of using the original feature as the input, we're going to construct another set of linear threshold units where the outputs of those units will send to this linear threshold unit to construct the final prediction. So say, to construct the first input of our final linear threshold unit, we're going to construct another linear threshold unit, which integrates the original data features and probably also constant feature 1 and do this dot product and linear thresholding. So the output of this particular linear threshold unit is sent to the second one. And the output of the first one is served as the input, the first input of the second one. Right? And similarly, we can construct another linear threshold unit, which are parameterized by a set of new parameters, and then do some transformation of the integration and transformation of the original data features and generates some output and use it as the second input of this linear threshold unit, which generates the final output. Right? So similarly, we can construct the third and the fourth linear threshold units, which provides the third input and fourth input for this final linear threshold unit, who is in charge of prediction. Right? So by doing so, by doing this kind of construction, we actually have built a two-layer feed-forward neural network. So why it's called two-layer? So basically, our two-layer feed-forward neural network consists of an input layer, a hidden layer, and an output layer. But because the input layer is kind of constant, they're provided from the data, so we usually do not count the input layer as into the total number of layers. That's why we call it two-layer, because it contains the hidden layer and also one hidden layer and one output layer. So we can view the values associated with the nodes on the hidden layers as some kind of representation of the inputs or some kind of transformation of the original features, right? So you can say the first input, the first set of nodes in the hidden layer are actually one kind of linear combination thresholding from the original features, right? And the second input, my second set of nodes, these two nodes in the hidden layer actually conducts another linear transformation and thresholding, right? So these operations are parameterized by a different set of weights. So please don't be confused, right? So, so you can view the hidden layers as some kind of feature representation, right? And those new feature representations will serve as features and then sent to our output layer to generate final output. So now I want to ask that this output, is this output of this two-layer neural network still linear to the original input features?
I think yes.
Yes, why?
Because the combination of two linear functions is a linear function.
Yeah, that's some kind of good point, but it's still a bit incorrect. The reason is that we are not only do some linear combination. So linear combination is only done in this dot product nodes, right? But after the linear combination, we send this score into a thresholding unit. So this is actually a sine function over the linear combination. So through this thresholding, unfortunately, it does not maintain the linearity, right? Because whether you're positive or negative is not linearly to the feature values. Right. So here I want to emphasize that. Why? Because although our original unit, right, looks very simple, right? But just by this simple rule to stacking them together and to concatenate them together, even two layers, you will end up with a very different classification function. And later we'll see the classification boundary. Okay. So in the neural network literature, we usually, for succinct, we usually do not separate the dot product and thresholding. Instead, we just merge them together into one node. We call this node as a neuron. So then if we can count how many neurons in this two-layer network, we say, okay, there are 1, 2, 3, 4, 5. There are actually 5 neurons. So 4 are in the hidden layer, and 1 are in the output, is actually the output node. So if we want to further, increase expressiveness of this neural network, what can we do is that we can further replace the input node in the input layer by the output of a third of another linear threshold unit. So by doing so, we can make a 3-layer network, right? So we can do this continuously. Like we can construct an actually deep neural network. So that's why it's called deep neural network, because if you can use same kind of rules by stacking a set of neural network to form 1 layer, and then use the output of 1 layer neural network as input of another layer to add 1 more layer. So you can add whatever numbers of layers you want to construct very deep neural network. Okay. So now, before we talk about the details about training calculation regarding neural networks, let us give some formal definition and description of the neural network. So in general, neural network modeling and training can be viewed as a type of very robust approach to approximate all kinds of value functions. You can use neural network to approximate real value, discrete value, the vector value functions. Actually, all those type of functions are very widely present in real applications. You'll see many neural network applications. And neural networks are among the most effective general purpose supervised learning methods currently known. So I think you have heard a lot of news about artificial intelligence. They're mainly trained and they're mainly trained by neural networks. So the cornerstone of the neural network is the backpropagation algorithm. So all the modern training algorithms for neural networks are based on backpropagation. So it is shown to be very, very successful. And also the backpropagation is the key topic we want to discuss in neural network. So everybody should be able to derive the backpropagation, should be able to implement the backpropagation algorithm from scratch. That's our requirement. Okay. So, but I want to mention that the artificial neural networks, their invention is enlightened from the biological neurons. So this is the first drawing of the brain cells by biological scientists. So people found that the neurons consist of several key parts. One key component is called dendrite. Those kind of things are you can view as some integrator or something, like it can collect information from other neurons. And then between neurons, there's another component called axon. You can view it as a biological component that can send out pass the biological signals or information, right? So see, the architecture of the neural network are inspired by the dendrites and axon. But here I want to emphasize, at most we can say the modern artificial neurons are inspired by biological neurons, but never view them as some close relatives or whatever. Actually, any serious neuroscientist, I mean biological neuroscientists, they refuse to admit any closeness between the artificial neural network and the biological neural network, because artificial neural network like many fundamental functions in biological neurons. So don't take the similarity seriously. So you can just use that as an analogy, but it's not a rigorous analogy. And then how is an artificial neuron defined, right? So you can view it as a type of function, a specific type of function that very loosely mimic a biological neuron. So the input of an artificial neuron is a collection of input. So you can view it as an input vector x. And to construct to compute the output of an artificial neuron, you'll need to do 2 steps. So in the first step, you apply a dot product with the weight w and add the bus parameter b. This is very similar to the prediction score for linear classifier. It's not very similar, it's exactly the same. It's just a linear prediction score. And in the second step, on this score, you will apply a transformation. So this transformation is called an activation function. That means to compute the output of a neuron, you first compute a linear prediction score on that, and then compute the activation function of this score. That's the way we compute neuron. Does it make sense?
Is something like sign, is that like an example of what an activation could be?
Oh yeah, we are. We'll introduce it right now. But yeah, any function can be used as activation function. A sign obviously is one value function, but it's not often used. Any other question regarding the definition of the neuron?
So the active function is same to the threshold function in the neural network?
It's not. Actually, the thresholding function we just mentioned, right, is a particular type of activation function. You have many other choices of activation function. For example, tanh, for example, sigmoid, for example, ReLU, which we mentioned. Those are very popular activation functions. Actually, sign function is not very popular. It's just often analyzed in a theoretical perspective of neural network. If you analyze it with other like tanh, it's way more complicated. Other question? Okay, so I assume everybody is on the same page, right? Because neuron is the very basic component of artificial neural network. All the neural networks are constructed by how do you organize a bunch of neurons. The number of neurons can be, in a modern neural network, can be like hundreds of thousands or millions or even billions. Okay, great. So let us look at the linear threshold unit, our previous example, right? So we can see that these 2 nodes actually fulfill 1 neuron, right? So for the inputs are those 4 features and constant feature 1, right? So when we compute the output of this neuron, we'll first do this dot product, right? To compute the W transpose X plus B, and then we'll apply a thresholding function on this. So the thresholding function is actually the activation function used in this linear threshold unit. So other activations are possible, right? So here are a few common use activation functions. So the simplest one will be the linear unit. That means you actually don't do any nonlinear transformation of your prediction score. You can just remove the activation function. But it is equivalent to like I use the activation function to be itself, right? And thresholding or sign unit is this function, as we just mentioned. But here, these three are the state-of-art neural networks, what the state-of-art neural networks often use. So the first one is called sigmoid unit. So it's 1 over 1 plus exponential to the power of minus z. So the benefit of sigmoid is that for arbitrary score, real score, it will squeeze this score into a range of the range between 0 and 1. Right? Because you see that exponential of this number is always non-negative, right? So 1 over 1 plus some non-negative numbers will always be less than 1, less than or equal to 1 or bigger than or equal to 0. So the benefit of sigmoid is that just squeeze the signal to ensure that it will be between 0 and 1. You won't propagate your signals to make it larger and larger, and then some numerical error appears. Right? Another commonly used activation function is called rectified linear unit. So it was proposed very recently, about like 10 years ago, I believe, around 10 years ago. So it soon becomes very, very popular. So this is just the max function, 0 and z. It's similar to the hinge loss, right? 0 and the score z. And although this is a max function, but when you plug in this rectified linear unit, your whole function of neural network will become highly nonlinear. And also, a third commonly used activation function is called tanh. So the tanh can ensure that after applying tanh, your signal will be between -1 and 1. So actually, you squeeze your signal in this -1 to 1 to avoid your signal to be amplified to be like ridiculously larger. Right? This actually has the same function of the sigmoid, but tanh is more, right now it's more often used than sigmoid. Sigmoid was invented about like 1980s. At that time, it was quite frequently used, but right now, tanh and rectified linear unit seem to dominate the choice of activation functions in frontier research. Okay, but there are many more like Sinusoid, sonic, Gaussian, polynomial, whatever. So now let us look at the neural network. Right? The neural network you can build as a function that converts the inputs to the output. This function is defined on a directed acyclic graph. So basically, the nodes are organized in layers, so layer by layer. So each node corresponds to a neuron. So that means if you want to compute the output of the node, namely a neuron, you have to follow 2 steps, right? As we just mentioned. And the edges on this neural network carry out of one neuron to another neuron. That means it connects neurons. And on the edges are associated with weights. So here's one concrete example. Right? So this is a 2-layer neural network. So we have one hidden layer and one open layer. So remember, as we mentioned, we don't count input layer as in a total layer number. Right? So you can see there are a lot of edges, right? So each edge connects a pair of the nodes. So usually, people just connect nodes in successive layers. So you can say this edge connects one node in the input layer, and then one node in the hidden layer. And this edge connects one node in the hidden layer, and then one node in the output layer. But I mean, again, there's no strict restriction in defining in the definition of the edges. You can definitely construct one edge from this node in the input layer to the output layer. This is called skip layer. Or no, this is called skip connection. So each edge is associated with a weight. Later we'll introduce how we index those weight. So in general, if you want to define a neural network, we need to specify three things. So first, what is the structure of the graph, the network, right? So how many nodes, how many layers do you want to use, right? How many nodes are used to construct each layer, and also how those nodes, how between those nodes are connected. And the second thing you need to specify is the type of the activation function you want to assign, like sign function, like sigmoid, 10H, or a loop. Right? You need to choose them beforehand. And finally, you need to set the values of the attributes. Right? So the structure of the neural network and also the type of activation, they are usually referred to as the architecture of the network. So typically, they are predefined before the training procedure. And the estimation of weights are learned from data. So basically, if you say I want to train a neural network from data, we mean to estimate the weights on those network. But before the training, we should be clear about the architecture of our network, including the structure and also the type of activation function. So here I want to emphasize that because of complexity of the neural network, the architecture of the network, also the choice of the activation function jointly, are showing to be very sensitive. No, I should say it reversely. So the performance of the neural network in many, many tasks are showing to be very sensitive of the architecture of network. Namely, how many layers do you choose, and how do you build up the connections between the nodes, and how many nodes do you choose, and also type of activation functions. So that actually stimulated another branch of research they call meta learning. So basically, how do you avoid manually tuning those architectures, because it's really exhaustive and it's really hard, right? And people are trying to use machine learning method to find to efficiently find the best architecture for a network. It's called meta learning. So if you're doing something regarding neural network, I would suggest you to investigate some meta learning package. They are actually open source package. You can call them to optimize the architecture of neural network. And then the training are done by the backpropagation. So when we talk about backpropagation, we're saying how we efficiently calculate the gradient of those weights and update them. Okay. Any questions so far? Great. So here's a brief history of neural networks. So when I talk machine learning, I have taught this course a few years. So there are always some students come to me and express their passion on artificial neural network and saying, okay, why not we focus totally on this newest research? But I would like to point out, actually, the neural networks were invented many years ago. So it was invented much earlier before I was born. So you can say, if you trace back very early, these two pioneers, they showed how linear threshold units can compute logic functions. It's in the 1940s. In 1949, Hebb, he's a famous psychologist, and he suggested a learning rule that has some psychological plausibility. Then in the 1950s, Rosenblatt invented perceptron. So actually, he invented a learning algorithm for the linear threshold units. They won't specifically call it a linear classifier. In 1969, Minsky and Pepper studied the neurons from geometric perspective. In the 1980s, convolutional neural nets. So right now, all the image applications are, I believe all the image applications are dominated by this convolutional neural nets. They were invented by a Japanese scientist and Kun, and also in the 1980s, the backpropagation algorithm, as actually the cornerstone of the modern neural network, has already been invented in the 1980s, about 3 decades ago, right? And from 2003 to today, it is the the prosperous time for the model neural networks, because people found that we have powerful machines, we have GPUs, we have big data, and people found out, okay, if I combine this powerful computation resources and huge amount of data, we found that neural network is really doing an amazing job in many challenging tasks. So if you want to know more gossip about neural networks, look at this slice. This is summarized by another pioneer, Eugen, is a European neural networks researchers. He invented LSTM. You can look at more, because a lot of arguments in neural network literature and debates. Okay, so before we talk about the details about how to train neural networks, we would like to know how expressive neural networks are, right? So when people talk about deep learning, we'll say, okay, deep learning is very powerful, but how powerful is it? Right? So to give you a concrete example, we still start with the linear threshold unit. Right? So a single neuron may name a single linear threshold unit, right? So we know that the classic boundary is just a line, right? If it's three-dimensional space or n-dimensional space, it's a hyperplane. It's just basically just linear. But if you construct a two-layer neural network using linear threshold unit, if you look at the clustering boundary, you see it's no longer nonlinear. It's no longer linear. So actually, the clustering boundary is showing to be a convex polygon, but it's just one convex polygon. Right? Next, if we add one more layer, still this one more layer are still may still consist of linear threshold units. The clustering boundary becomes like this. So you see, they are a set of convex polygons. So it's showing to be a unions of convex polygons. So you can see that just use simple rules, right? Use very simple unit, and build up neural networks layer by layer. You can see the clustering boundary becomes more and more complex, implying that the function it can model can be more and more complicated. So we have some beautiful theory in hand. It shows that in 1989, it shows that any continuous function can be approximated to arbitrary accuracy just using one hidden layer of sigmoid units. Basically, if you just use sigmoid function, sigmoid activation function, you just construct one hidden layer, and you can use this artificial neural network to approximate arbitrary function. As long as the neural network to be enough wide, it can approximate any continuous function to be an arbitrary accuracy. So you can see how flexible it is. Right? So further, in 1993, people show that this approximation error is insensitive to the choice of activation function. That means the result is not limited to sigmoid unit. You may actually use 10-inch. You can use square root. It doesn't matter. So one concrete example: if you use two-layer threshold networks means that you use this sum function, right? Now linear threshold unit. It's showing to be it can express any Bloom functions. So now I want to ask, if you just use one linear threshold unit, can it express any Bloom function? What kind of Bloom function it cannot express? An idea? Yes. Excellent, right? That means, okay, everybody are on the same page. Everybody has a memory for what we have discussed previously, right? We mentioned that when we analyze the expressiveness of linear functions, we use Bloom function as an example, right? For a few Bloom functions, yes, they can be equivalently represented by linear classifier, but one particular counterexample is XOR function, right? XOR function cannot be represented by any linear function, but if you just stack two linear functions, two linear classifiers together, I mean, using the linear threshold unit to construct two-layer neural network, right? Now the expressiveness is dramatically improved, right? It can approximate any Boolean functions, including XOR. So here are a few results about the VC dimension. This is the VC dimension for threshold network, and this is VC dimension for sigma networks. This is the upper bound, lower bound. But anyway, you can view that this VC dimension are related to the size of network, right? So now this absolute value means the size of the edges, number of edges. Right? So you can see that from the result you can see that the larger the network, right, the more edges the network, the more expressive network. But in the meantime, we know that the more expressive network model, it more easily overfits the data. Right? So this is also another issue of the neural network. Although it's very powerful, at the same time, it's very easy to overfit to the training data. So people have developed a lot of methods to regularize the neural network to avoid overfitting. So to deepen our understanding of the neural network, so I want to leave an exercise for you. This might be the homework for homework. This might be the one question on homework 5, last homework. Okay. So I want you guys to try to show that if we have only linear units, basically our activation function just x. It's not thresholding, not sigma, just x. Then multiple layers does not change the expressiveness. So try to think about that. Right? It's very, it is a bit straightforward, but you need to think about that. Okay, any questions so far regarding the definition of neural networks? Okay, great. So now let us talk about how the computation regarding neural networks. Right? So we're going to first talk about how do we efficiently make prediction with the neural network model. So this procedure is also referred to forward pass. So as we mentioned, right? So the topic of neural network consists of 2 components. First, the definition of neural network, the general description. The second, we're going to introduce how do we make prediction with neural network. And then our focus will be on how to train the neural networks with backpropagation. But how to do the prediction is a prerequisite. We need to know how to do that. Right? Otherwise, we cannot do the training. And finally, I'll give a few practical concerns. But by the way, I want to mention that in the next week, we'll give a tutorial about TensorFlow and also possibly including PyTorch. So I would highly encourage you guys to attend the online lecture because this is very, very useful. Although in our course requirement, you are demanded to implement backpropagation from scratch, but in practice, you'll never need to do it by yourself. But in practice, you always need to take advantage of the modern libraries to do everything. You do not need to revamp the wheels. Right? Okay, so how to make prediction? So we'll use one example network to illustrate. Right? So we have this 2-layer neural network. We have one hidden layer and one output layer Y. So our input feature consists of x0, x1, x2, and the hidden layer consists of z0, z1, z2. So the dashed nodes, x0 and z0 here are just constant feature 1. Okay? So don't be confused because we introduce them just to introduce the bias parameter. Okay? So here we, before we do the computation, we need to introduce some naming conventions because there are a lot of weights and layers associated with a neural network, right? To avoid confounding different weights, we need to make clear conventions beforehand. Right? So we represent the inputs by x, and the nodes in the hidden layer, or neurons in the hidden layer by z, and output by y. Okay. And as I just mentioned, right? So for each layer, we introduce a bias feature, which is constant. It's always 1. So they're dashed. They're not dashed. They're just with some light dark color. And And to compute the neuron, the value associated with each neuron, we'll apply some activation function. We will give some detailed description about the sigma activation function, like how do we compute the gradient of the sigma activation function. And for each hidden layer, the neurons, the value associated with each hidden layer, we need to conduct 2 steps, right? First, we calculate the linear prediction score, and then we apply this activation function, say sigma, right? But in the final output, here I want you to pay attention to, we do not apply any activation function. We just do a linear combination of this input, Z0, Z1, Z2, and then output, right? Or in other words, you can view it as a linear activation function. Right? Is everybody clear? Any question? So this is a convention of the neural network. So basically, for every layer other than the output layer, the neuron, the output neuron is computed in 2 steps. The first step is to do the linear combination, the dot product for all the weights, all the features connected to this neuron, and then apply some nonlinear activation function, whatever, right? But in the output layer, you just do a dot product. You don't do any nonlinear activation function. Or in other words, you can view it as you perform a linear activation function. Someone may ask why, right? Why is it necessary to do that? I can only tell you this is a convention. People view the output just a linear combination of the outputs of the neurons in the second last layer. If you feel upset of that, you can apply nonlinear activation function. This is totally valid, but following the convention, we just use this convention. Does it make sense? Okay. So now I will introduce how we index each weight on the neural network edges, right? So to clearly index each particular weight, we use both subscript and superscript. So in a superscript, we use the target layer. So the target layer means that where the index of layer this associated edge points to. So say for this particular weight, right? We see the edge it stays on, connects to or points to the output layer, right? So the superscript we use O. O represents output layer. And we can take a look at this particular weight, right? The edge this weight stays on, points to the hidden layer, right? So the target layer is hidden layer. So the superscript for this weight is H, represents hidden layer. Does it make sense? Right? Of course, if you have multiple layers, we can also index each layer by 1, 2, 3, 4, 5. Then we just replace the target layer by the layer number where the corresponding edge points to. And then for the subscript, we use 2 indices, which represents where the edge comes from, and where the destination, the edge points to. Right? So take this. I would like to use this weight as an example, right? So this weight, the corresponding edge, connects from the node or neuron 2 in the input layer to the neuron 2 in the hidden layer, right? So the from node is indexed by 2, and the target node or destination node is indexed by 2. That's why the subscript is 2, 2, right? The from node 2, from node number is 2, and the destination node number 2. Okay? So similarly, we can take a look at this, right? So the subscript indicates where the from node and the to node are, right? So this associated edge connects neuron 0 from the input layer to neuron 1 in the hidden layer. So the subscript is 0, 1. And the superscript, because the target layer is in the hidden layer, so we use H. Does it make sense? Any question regarding this definition, notation? Okay, I assume everybody is comfortable, right? If you feel uncomfortable, just let me know, right? So for this output layer, because we only have one output neuron, and we index this output neuron as 1. That's why we say this weight is denoted by W0, 1, oh, rather than W0, 0, because we index this sole output neuron as neuron 1. So similarly, we can say this edge, it connects neuron 1 in the hidden layer to the neuron 1 in the output layer, right? So it's W11, the target layer is O, right? W210. Okay, so after we making sure the notations of those weights, let us talk about how we conduct the computation. So given an input x, suppose x are in your hand, and suppose we have our weight values, right? And we want to know how do we compute output, right? So the computation is from bottom to the top, right? We start from the input layer, then we sequentially compute each neuron in the upper level, and after we finish computation of each neuron in this upper level, in this upper layer, then we integrate the value of the neurons in the upper layer and to calculate the neurons in the next layer. We do it layer by layer until we reach the top layer. So this procedure is called forward pass because we view the order from the input to the output as a forward order. So, so you might connect it to the back propagation. Back propagation, the computation will say the computation order is from the output layer to the input layer. That's why it's called back propagation. Okay, so let us first do the forward pass, right? So as we just mentioned, we're gonna first starting from the input layer, we're gonna first compute the neurons in the hidden layer, so Z1 and Z2. Right? So Z1 is computed by first do a linear combination of the input features which connect to Z1. Right? So all the 3 input features connect to Z1. So we do the linear combination. So it's W0H multiplied with X0. As we mentioned, X0 is a bias feature, it's constant 1, so we never need to explicitly write it down. And then for X1, the associated edge weight is denoted by W11 connects 1 to the 1, right? W11H, that's where it comes from, right? And multiply with X1. And the W21H, right? Because it connects from X2 to Z1, right? So the subscript is 21. And the target layer is hidden layer. So W21H is the weight associated with this edge, then multiplying with the input feature X2, right? And then after we get this prediction score, we apply our activation function. Here we choose sigmoid to get the neurons value Z1, right? So similarly, we can compute the neurons value Z2, right? So again, we first do a linear combination of all the features connecting to Z2, right? All the features X0, X1, X2, they connect to Z2, and associated with each feature are a set of different weights. So you can see that the weight on the edge connecting X0 and Z2 are denoted by W02H. So you can see W01H and W02H are two biases. So be clear, in the neural network, one bias feature can be assigned with multiple bias features. They're determined by how many edges connecting this bias feature to the nodes or neurons in the upper level. Okay? Any question?
What about Z0?
Yeah, I will talk about later. Same thing, you apply the same rule. Any other question? Okay, great. So we'll apply the same rule to compute Z2, right? We do a linear combination of x0, x1, x2. So their associated weights are denoted by W02H, W01, W12H, and W22H, right? And then you apply the activation function to get the neurons value Z2, right? So now we have finished computation of the neurons in the hidden layer, right? Remember, Z0 is 1. We do not need to compute it. Right? And finally, because we have only 2 layers, right? And we integrate all the neurons values in the hidden layer to compute the output neuron. Right? So the output neuron is computed by just do linear combination of the neurons in the hidden layer. W0O, right? Which is on the edge connecting Z0 to 1, right? Again, Z0 is 1, so you don't need to write 1 explicitly here, right? Then W11O multiply with Z1 and W21O multiply with Z2, and add them together you get 1. So here we do not apply any nonlinear activation function. So now I want to ask, right? If I have another output, like I do not have, I have 2 output neurons, right? Does Z0 will be multiplied with the same weight, W0O. Any idea?
You can use half of that for each of them.
I can use what?
Half of that.
Half of Z0?
Yes, half for one neuron and half for the other.
Well, I think, yeah. I think your suggestion is kind of interesting, but we actually do not need to be that complex. So if you have a second output neuron, you have another 3 edges to this neuron. Right, let me write it down. So probably that will be better. Oh, oops. Let me insert my iPad. Okay, can anybody see the pad? Right? So we just mentioned, because in our simple example, we have only 1 output neuron, right? So now my question is that if I have another neuron as the output, that means my output layer has 2 neurons, right? So you can imagine your output is a vector. You have multiple outputs, right? So how do we compute the second output neuron's value, right? So you just follow the same rule, like you have a Y2, right? So that means your neurons in the hidden layer, they're gonna have another 3rd edges connecting to Y2. And correspondingly, associated with those new edges are a set of new weights. So you say 0, the edge who connects Z0 and Y2, they will be denoted by 2, the subscript is 2, 0, 2, and O, right? Because it is the target layer is the upper layer, right? So this edge, which connects Z1 to Y2, is denoted by W1 to O. And this new edge, which connects Z2 to Y2, denoted by W2 to O. So those three weights are completely different from the previous weights. And we will compute it, Y2, you just follow the rule. W02O plus W1 to O times Z1 plus W2 to O times Z2. That's how you compute. That's how you compute the value for the other alpha neuron. Just follow the rule, nothing else. So, yeah. Is everybody comfortable with this? Is there any question? Okay, great. So,
Excuse me.
uh-huh.
How can we measure the number of neurons in each layer? How should we decide on the number of neurons?
That's a very good question. So actually, there's no strict rule telling you how to decide. They're totally dependent on the applications. So let me tell you the typical application of the neural network. So I'm going to construct a 3-layer neural network where I just, from my guess, I will put 10 nodes in the hidden layer 1, 10 nodes in hidden layer 2, and 1 node in the upper layer. That's it. And I use sigma activation function. I will just run back propagation and say what's the performance. If the performance is not satisfactory, I'll go back and think about whether, oh, it looks like probably my layer width is too narrow. I'm going to increase the width of layer to be 20. That means I use 20 neurons in layer 1, 20 neurons in layer 2, and run again and see whether the performance increases. If not, I'll go back to, say, try another activation function. So there are a lot of settings, architectures you need to adjust in practice. Does it make sense?
Yeah, and another question, does overfitting applies in a neural network?
What?
Overfitting, do we have overfitting in neural networks?
Yeah, as I mentioned, neural network is very expensive, so it's very easy to overfit data. It's actually the major issue, the major complaint about neural network is it is too flexible. It's so easy to overfit to train data. You have to apply all kinds of tricks to alleviate the overfitting phenomenon. Maybe you have heard before, like dropout, like early stalking, and third validation set. Those are all the common used tricks to alleviate overfitting.
Thank you.
Mm-hmm.
Thank you.
Okay, great. Any other question? Okay, so yeah, that's basically what is the forward pass. So to conduct any, if you have a neural network in hand, you have all the parameters in hand, if you want to make a prediction, the general procedure is to compute the scores and neural values layer by layer. You start from the input layer, and then sequentially compute the neural values in each upper layer, and then use each upper layer's neural values to compute the neural values in next layer, and layer by layer finally reach the output. So this procedure is called forward pass because we define the order from the input layer to the output layer as the forward order, right? And obviously, when we compute in the reverse order, we call it backward order. Okay, so now let us look at the backpropagation. I need to switch to the slides. So now let us talk about how to train neural networks. Right? So everybody is able to see the slides, right? If you cannot see it, let me know. Okay, so neural networks are trained mainly by back propagation. So again, like we have introduced the definition of neural networks, the expressive neural networks, how do we conduct prediction, right? So now our focus will be how to train neural networks. So let us first formulate the training of the neural networks, right? So suppose we are given the network architecture, and which includes the layout of neurons, how they're connecting with each other, and also the type of activation function. Right? And also we have collected a data set of label examples, which can be viewed pairs of the input and output. Then the goal is to learn the weights of the neural network. Right? So for fixed architecture and also the fixed type of activation function, we can view a neural network as a function parameterized by the weights associated with the network. Right? So basically, you can view the prediction y as a function of the input x and also the weights. So from this point of view, you can consider linear function, right? Linear classifier as the prediction of linear classifier as a function of x and the feature weights as well. Right? So you can view them in a unified way, right? So that means we can consider the classifier neural network as being completely defined by its weights. So to learn the weights from data, we can define a loss function on the training data, right? So we compute the loss of each training example and add them together to get the loss on the training data. Then we minimize this loss function with respect to the neural network weights. Perhaps we add some regularizer just like SVM, right? So you can see this training protocol or strategy is the same as that for other simpler classifiers like SVM, like perception, like this mean square method, right? And those methods are all linear models, right? But again, we can apply the same kind of approach for nonlinear methods. So let's look at a concrete example, right? We still use this example neural network to illustrate it. Right? So suppose we have a set of weights in our hand. Right? There could be some weights randomly initialized, whatever, right? So now we're given a training input x. So then through this forward pass, we can compute our prediction, the value of the output neuron, y, right? And suppose we have the true label, we have the training label, which is y star, right? And to define a loss, we can write a square loss. Right? So this is the most common used loss for neural network. The square loss is just square of y, the prediction, minus the ground truth, and then take the half. Right? So, and then we can compute the square loss using neural network output to predict every training example, right? And then add them together to get our training square loss on the training data, right? And then we minimize this square training loss to estimate optimal weight parameters. Then the remaining question is how do we solve the optimization problem? Right? How do we solve it? An idea? How do we solve it? Yeah, I saw some suggestion. Gradient descent, right? Yeah, gradient descent. This is a function. Nothing different with the previous prediction function, right? The only difference is that, okay, this function can be way complicated, right? But it's still a function. Right? We can compute gradient or subgradient. So now let us look at, of course, to scale your learning procedure to large data, we prefer stochastic gradient descent, right? So let's just review this framework again, right? So our loss is here. It's defined on all the training data. So the training data are denoted by S. So we're going to initialize the parameters of the neural network weights. Then we go through the whole data set for t epochs. And then inside each epoch, we first shuffle the training set randomly. And then we process each training example, right? To process each training example, we treat this training example as the entire data set, then compute the gradient of the loss on this fake training set, right? And this gradient is the stochastic gradient. Then we update the weight of the neural network, the weights of the neural network, by subtracting the stochastic gradient multiplied with some learning rate gamma t, right? So it's the same framework as our stochastic gradient descent for support vector machines or for least mean square method or perceptron, right? The same thing. So again, gamma t is learning rate. So you have many tricks possible. So if you want your learning, if you want to choose a good learning rate, you have to manually tune some parameter. For example, the parameters released in your homework, right? So any questions so far? I assume everybody is familiar with this. We just reviewed the old framework. Okay. So, but here I want to mention something very important in practice. So first, this is different from SVM's objective function or least mean square order objective function. This objective is not convex. General is not convex, and general is highly nonlinear. That means even you find some optimum, it is really not the global optimum. It's oftentimes the local optimum. So the initialization can determine which local optimum you finally reach. In other words, initialization matters as well. So it's different from SVM or other. If you train SVM, you can initialize your weight vector bus parameter arbitrarily. In theory, it all converges to the same global optimum because the objective function is convex. But for neural network, even use the same algorithmic framework to train, different initialization may end up with different local optimum and very different performance. So if you, in practice, if you apply neural network, you will see that in many modern neural network library, we have a variety of common used ways to initialize the weights, like XViver, like initialization. You can take a look at TensorFlow library. So they are summarized to, those common used method are summarized and implemented by others because they're shown to be good in practice. Okay. So can we solve everything? The answer is always not. Why? Because we haven't talked about how to take the gradient, right? So actually, all the other things are the same. We use the same framework, we use the same strategy to construct objective function and optimization, but the computation of the gradient is the key bottleneck of the training. Why? Because modern neural networks are really huge. So the deep learning, where does this, buzzword deep learning comes from? It comes from the deep architecture of neural network. For example, a recent paper used about like 150 layers for image classification. And if you're some researcher in the in computer vision, you must know the hottest recently very hot neural network called ResNet. ResNet uses 250 layers. So you can imagine how deep the network is. If you choose 100 if you choose 100 nodes in each layer, which is pretty small, and 250 layers end up with like 20,000 weights, right? Oh, sorry, it's not 20,000. It's actually 2 million parameters. And a million neurons in modern neural network is very mediocre. So in many large companies or large industry applications, people are getting used to, like in Google, people are getting used to train like billions of neurons. So if you want to remember, even use a stochastic gradient descent, every time you just process one single example, you have to compute this gradient, the stochastic gradient, with respect to 1 million weights. So computation is really expensive, right? Then the problem is how to address this problem, right? How do we avoid redundant computation, right? How do we maximize the efficiency of the gradient calculation? That's where the backpropagation stands. So before we introduce the details of backpropagation, we need to stop for a while, just do a checkpoint, right? So the whole training procedure is like this, right? Let's keep this general framework in our mind, right? So the training is conducted after we have identified the structure of the neural network, we have known the type, we have chosen the type of activation function. So, and also we can make prediction given any set of the weight values from input. This is called forward pass. And if we have the true label of the input, according to the prediction of our neural network, we can define a loss for that example, right? And if we have a set of training examples, we can define a loss function over the set of training data, right? And we take the derivative of the loss with respect to each weight, then we take the gradient step, right? If we just take the gradient on a small random set of examples, we compute the stochastic gradient step. That's the whole framework of training a neural network. So the key issue is how do we efficiently compute the gradient or the subgradient of the neural network weights. That's what the backpropagation algorithm tries to address. Okay? So any questions so far? Great, I assume everybody is on the same page. Okay, so I will give you a general sense. So essentially backpropagation is an application of chain rule. So we need to first review what is chain rule, right? So chain rule is the way to compute the derivative of composite functions, right? So suppose z is a function of y and y is a function of x. Then obviously z is a function of x as well. Then how do we compute the partial derivative of z over partial derivative of x? That's where we apply the chain rule, right? So we can graphically describe the dependency between z, y, and x, right? So as we just mentioned, z is a function of y, so we can connect y to z, right? And y is a function of x, we can connect x to y, right? So if you want to compute the partial derivative of z with respect to x, we can compute the partial derivative of z with respect to y, then compute the partial derivative of y with respect to x, and then multiply them together, right? This is the chain rule, right? That's how we compute the partial derivative of z over partial derivative of x, right? So in general, we can extend it for two variables, right? So suppose z is a function of y1 and a function of y2, and both y1 and y2 are function of z. That means, okay, z depends on y1, z depends on y2, and both y1 and y2 depend on x, right? To compute the partial derivative of z over partial derivative of x, we need to compute the partial derivative of z with respect to y1 and with respect to y2, respectively, right? and also compute the partial derivative y1 with respect to x, partial derivative y2 with respect to x, right? And then multiply them correspondingly and add them together, right? So that's how we apply the full derivative rule, right? Full derivative rule in the chain rule. So assume everybody is familiar with this, right? It's very fundamental in our calculus course, right? So in general, suppose z is a function of n variables, y1 to yn, and each of these n variables can be viewed as function of x. Then if you want to compute the partial derivative of z with respect to the partial derivative of x, we're gonna first compute the partial derivative of z with respect to each variable yi, and then multiplying with the partial derivative of each variable yi over partial derivative with respect to x, right? And then you add up all those product. You add up all those product together. Okay. That's how we apply chain rule, right? So now let us look at the application. We just gave a brief start, and then we'll give the detailed calculation on Thursday, right? So we know that through the forward pass, we compute the neuron values layer by layer, and finally get output value, right? So when we got output value, this output value is sent to the loss function, right? We get our loss function value. So if we want to compute the loss function with respect to any edge weight, say partial L over this weight, Wijo, and also this weight, any weight on edges connecting to the hidden layer, like Wij. How can we do that? We just apply the chain rule to compute the gradient along the way to the widths. And also we need to identify the set of hidden neurons which are related to the weights which we want to compute the corresponding derivative. And then we just apply the chain rule. And the backpropagation essentially calculate those partial derivatives from the top layer to the bottom layer. That's called backward order. And from the calculation, just catch all the results. Those results are reduced to compute the partial derivative with respect to each weight in the bottom layers. Okay, so I think we should stop today, and we'll give a concrete example on the next lecture, and then we will summarize the rule of the backpropagation in a general scenario. Okay, I'll see you on Thursday.